SwayamPrabha. Digital India. Educated India.
So, since this derivative is computed while following a particular material, this derivative d dt, or which is d dxj is called material derivative or substantial derivative. Material derivative or substantial derivative. And as you will see that this will appear almost in all equations in fluid mechanics, this substantial derivative. That is of course, because of our consideration of the Eulerian concept, because most often we are interested in properties of the material, flow properties of the material element, and this will come. And remember, this derivative is not applicable to velocity alone, it can be applied to any field variable. So, it can be applied to density, pressure, temperature, because all flow variables in Eulerian description is a field variable. So, for all flow properties or all variables, this substantial or material derivative may come. Now, look something special. Think the flow is steady. We have already defined the flow is steady when u is independent of t. Now, what will happen then? The first term is 0, but this it is not 0. This is not 0. So, steady flow, a steady fluid flow does not mean that it has no acceleration. You see, but that would be a little difficult to explain in Lagrangian description. So, you can write for steady flow, acceleration is not 0. Acceleration of fluid element is non-zero. This first term, which refers to change in velocity at time t, at the same position. The first term represents the change in velocity at a fixed position with time, change in velocity with time at a fixed position. This part is usually called the local acceleration. It is called the local acceleration. And the second part, which is a change in velocity due to the change in particle position from one special point to another special position. Okay. So, this is due to a real transfer of material from one position to the another and called convective acceleration. and in general these are called local change, this is called convective change. When it is change in velocity, of course, it is local acceleration and convective acceleration, but as I mentioned that this change may be for any other variable. Let us see if it is a change in density we are talking about this way, then of course, this will be local change in density and the other will be convective change in density. So, this is local change and this part is we will call it convective acceleration. And this part okay. At this stage, of course, we are not going to consider acceleration and why this acceleration will take place and all other different consideration. We rather discussed acceleration just to get this concept of substantial or material derivative, because while discussing with kinematics, that is what we are mostly interested in. In kinematics, we are not much interested in acceleration and the cause of it. The next we will consider what we will later on see, or what we will be using as one of the governing equation, but in this case we will just consider it as a kinematical aspect of the flow. This is a very well known physical principle, the mass conservation principle. We will see what this mass conservation equation tells us about the flow velocity. Now, consider to formulate the mass conservation equation, consider a control volume, that is a volume fixed in space, a volume fixed in space, and that is to this volume flow is just coming and going out of it. Flow is coming into this volume and again going out of it. That is what is control volume. The volume itself is not changing, it is remaining fixed in space and time. Okay. That is what is a control volume. Fluid is moving through it. Let us see, for the time being we will move to any general type of volume. For the to start with, let us consider a fluid, this volume to be bounded by surfaces which are parallel to your coordinate planes. That is, all the bounding surfaces are parallel to the coordinating planes, coordinate planes, not coordinating planes. That is, you can think of a cube type of volume element, where all faces are parallel to the coordinate planes or perpendicular to the coordinate planes, both can be called. Let us consider this simple thing first. You can say these lengths in each direction to be delta x, delta y, delta z, or delta x 1, delta x 2, delta x 3, whatever you call it. Let us say delta x, delta y, delta z. Okay. Now, how much fluid is entering through it and how much fluid is leaving to it? How much fluid is moving into it and how much fluid is leaving out of it? We can consider phase by phase. Let us consider this phase which is perpendicular to this x direction. You can name it say P Q R S, this phase. Let us say the flow is coming from this side. It does not matter, of course. How much flow is entering into it? Mass flow through that phase. Yes. Rho, little louder. Rho delta x. Is that the mass flow that is entering? No. Rho delta y delta z. No, per unit time. Let us forget about. So, rho u in this case the component which is parallel to delta x, rho u delta y delta z. Okay. That is the mass flow entering through this phase P Q R S. Now, what is the mass flow, let us say, that is going out through this opposite phase? Yes. Yes. The opposite phase, this phase. Delta y delta z is all right, the area of that phase still remains delta y delta z, but what about this quantity rho u? Again it is rho u. See, this rho u is changing over this length delta x. Rho u is changing over this length delta x. So, it should be rho u plus delta rho u, some change in rho u, and okay, to the first order of accuracy we can write that to be rho u plus d dx of rho u into delta x. So, through the opposite phase, okay. So, now for this pair of phase the net mass flow, there is the difference between the two, the net mass, what should we call, outflow. So, net mass outflow okay. Similarly, now if we consider the other pair of phases which are perpendicular to the y direction and z direction, and then sum them, that is the total mass outflow rate per unit, because all we are considering is per unit time. So, total mass outflow rate through all 6 phases will be how much? How much it will be? See, similarly, the phases which are pair of which are perpendicular to y, the pair of phases which are perpendicular to y, that will give this term to be d dy of rho v delta x delta y delta z, and the phases which are perpendicular to the z direction again will give d dz of rho w delta x delta z. So, when we add, it becomes d dx of rho u plus d dy of rho v plus d dz of rho w into if we consider a finite area, we can write this as an integral. For a finite volume, we can write this as an integration over that. This delta x delta y delta z is the volume element. So, for a finite volume this can be written as integration of this. By the way, are you familiar with this term which is within the bracket? Divergence of? No, it is not velocity. Rho into velocity. Yes. So, for a finite control volume we can write okay. Now, what is the mass of the fluid contained within the control volume? Rho dV integrated over V, if we for the entire control volume. Okay. And see, because of this mass outflow rate, this mass will also change depending upon if whether if the inflow is more than the outflow, then there will be increase in mass within the control volume. Similarly, if there is outflow is more than the inflow, then within the control volume mass will decrease. So, what is the rate of change of mass within the control volume? So, mass fluid mass contained in the sorry. No, sorry, all right. And how much will be this? This will be minus of this quantity. Agreed? We have considered the outflow here as positive. So, if there is outflow, then of course, the mass will decrease. So, they will have opposite sign. Now, this integration of course, can be taken into within the differentiation, sorry, this differentiation can be taken within the integration, because they are of different nature, integration with respect to spatial element and differentiation with respect to time. So, taking that inside, we have and as it is true for any arbitrary volume, is true for any arbitrary volume. So, this see this also can be written as this divergence of rho u can be expanded. The divergence of rho u can be expanded as a derivative of products, and this can also be written as okay. This is the expanded form of the divergence rho u, which is quite straightforward if you remember that this is what is divergence of rho u from here. Okay. Now, look to the first 4 terms of this and look to that substantial derivative. This is what is the substantial derivative of density. Okay. So, this means and this is what is divergence of velocity. So, this is an alternative form of the continuity equation. We can use either this form or we can use this form, whichever is necessary. For steady flow, this becomes what it is for steady flow. What is the mass conservation equation for steady flow? This is not 0, remember, here this is 0. So, we can write only this much for steady flow. Now, we will use it for with a general type of volume, okay, not a cuboid type of volume. Look to this term. See, in each case, how did we get the mass inflow or mass outflow rate? See, mass inflow or mass outflow is also a vector. It has 3 components, rho u, rho v, rho w, or rho u 1, rho u 2, rho u 3. In each case, you can see that we are taking the component which is normal to that face, is not it? So, for the face which is normal to x direction, we have taken the x component and multiplied with the normal component of that area. So, actually this mass inflow rate or outflow rate, whatever you call it, it depends only on the component which is normal to that face. Okay. Now, consider any general volume, let us say any general volume any general volume V, which is bounded by an area A. The surface is bounded by surface area A and this volume is V. So, once again the change in mass within this volume is again that same thing. The rate of change of mass within the volume V is once again d dt of rho dV is how much? See, the net mass outflow or inflow, we can simply write it integrated over the entire area. Okay. Or in our index notation, sorry, the minus will be of course there, rho u j n j d. We can use the divergence theorem again to change it to a volume integral, which makes it or in vector notation that is the index notation for divergence. And once again this gives the same thing. We will be later on seeing that this is one of the important governing equation of our fluid dynamics. This is the mass conservation equation. However, in fluid mechanics it has a very popular name and people often call it by that name, which is continuity equation. So, this is we will call it mass conservation equation, which is really the correct name. Now, can you say what does this divergence of u mean? What is divergence of u? let us say to look to this divergence of u, consider a material element and think about a small element only, a small material element, and to differentiate the volume with V, because V we are fixing the volume as a just a volume in space. So, we will differentiate it with respect with the material volume. Material volume is just a volume found by a certain material. This may occupy different position in space. Let us call this material volume element. So, consider a material volume element V. Let us call this tau, material volume element, and it is bounded by a material surface, and again instead of calling it A, we will call it another name, bounded by the material now, let us say that the material surface is moving. The material surface is moving either inward or outward, or is deforming. We can say the material surface is being deformed. What will happen as a consequence? If the material surface, think about just a material, this is no longer just a volume, it is a material volume made up of only certain fluid elements. Its volume will change. If its surface moves outward or inward, or if the surface deforms, then its volume will change. So, you can then write that d tau dt is what? How much the volume is moving, how much the total surface is moving, and that is again which again by divergence theorem sorry, why rho? There is no question of rho, sorry. We are considering the movement of the surface. So, there is the surface velocity is the only thing that is required. So, the rate of volume change is sorry not dV, d tau. Now, take this rate of change of volume per unit volume. And sorry, will this minus be here? Will this minus be here? Will this minus be here? It will be plus, because if the surface moves outward, its volume will increase. So, this is no minus, plus. This is rate of change of material volume divided by the volume, or rate of change of volume per unit volume. If we consider this element to be very small infinitesimal element, that is approaching this to be 0, then this becomes this. Now, what is the left hand side? This is very familiar to you. Or let us say, what is rate of change of volume per unit volume, or change in volume per unit volume? Change in volume per unit volume. That is not compressibility. Change in volume per unit volume. Okay, change in length per unit length. Strain. Change in length per unit length is strain. So, change in volume per unit volume is volumetric strain. And this is of course not strain only, it is rate also. There is a rate involved here. It is not simply delta tau by tau, it is ddt. So, this is the left hand side is rate of volumetric strain, which is usually called as rate of expansion or rate of dilatation. So, this side is rate of volumetric strain. Or expansion or rate of dilatation. So, that is what is the meaning of divergence U. Okay. That is rate. That is what, instead of calling time rate, it is called simply rate. Because that whenever you say strain, that the special rate is already included. In strain is always increase in length per unit length or increase in volume per unit volume. So, the special rate is always included in it. So, when you in addition say rate, it is the time rate, that is what is meant. And you can see also that this velocity can also be called as rate of strain. or rather velocity gradient. Velocity gradients can be called up strain rate or rate of strain. This you can very easily see if you consider a small, say as an example, a small line element extending from point P to Q again, where at P the velocity is u, at Q the velocity is u plus delta u, or u plus du dx into delta x. Delta u is du dx into delta x, and then you can see that over a small time interval this element will elongate and the rate of strain will be du dx. You can consider a small time element delta t, so that the point P is moving from u to another location given by u into delta t. The second point Q is moving to a distance u plus delta u, u plus du dx delta x into delta t. So, you see that the 2 points of the same element is moving by different distance. That means, the element has extended or stretched. So, how much the 2 points have moved? If you take the difference of those, that you will get how much is the total strain, and from there you can again find that the du dx is strain rate. So, now let us think about the equation in this form. The continuity equation or the mass conservation equation in this form. We will define some flows to be incompressible, where density is independent of pressure. Remember this very clearly. Density is not constant. It says the density is independent of pressure. An incompressible flow is defined when density is independent of pressure, not that density is constant. A constant density is not an essential requirement of incompressible flow. Density may change in incompressible flow. So, the two most common mechanism of or reason of change in density, one is of course by pressure, the other is by thermal reason, thermal conduction. That also can cause change in density, even when there is no change in pressure, but there is considerable thermal conduction, then also the density can change, which is quite well known to you, which is almost every time you are experiencing that change in density due to thermal effect. This is not excluded in the definition of incompressible flow. Change in density by thermal reason is allowed in incompressible flow. I know whatever I say, still many of you will continue to keep on saying that incompressible flow means density constant, but to be precise it is not so. Incompressible flow needs that density is independent of pressure. Now, we know that at least if you are concerned with gas, that for gas at least it is not true. The gas density is not independent of pressure, but we will see that under certain circumstances which are not that very uncommon, okay, the change in pressure is so small that the change in density caused by that pressure change is really negligible. That if the density changes are really very small compared to the actual absolute pressure, sorry, the pressure changes are so small compared to that absolute pressure, then the density change that will occur due to that small change in pressure is practically negligible. That situation comes quite often, and in such a situation, even for gas, we will see it later that density is almost independent of pressure. So, we can further elaborate our definition of incompressible flow, that is, the incompressible flows are those flows where pressure changes are so small that the consequent change in density is negligible. Okay. And that is even in case of flow of gas is not really uncommon. There are many situations where changes in pressures are really small. Now, in addition, of course, if the thermal conductions are also very small, there is not much of temperature difference. Okay. Even then, the density change due to conduction, thermal conduction is also negligible. If that happens, the pressure changes are also very small and the thermal changes are also very small, then of course, density can be assumed to be constant. And what will happen in that case? Let us say that we have an incompressible flow in which even thermal changes are also negligible. Look to this continuity equation, what will happen to it then? And what will happen then? Look to the continuity equation. The continuity equation then gives what? Divergence of u is 0, or and what does it mean? Divergence of u already you have seen is rate of expansion, rate of expansion or rate of volume change, volumetric strain rate. So, an incompressible flow means that rate of expansion or rate of volumetric strain is 0, and you see that is the meaning of the word incompressible, something which cannot be compressed. Rate of volume change is 0. this any vector which satisfies this relation, that is divergence of that vector is 0, those vectors are called solenoidal. Okay. Any vector whose divergence is 0 is called a solenoidal vector. So, for an incompressible flow, the velocity vector is solenoidal. Or divergence free. Solenoidal means divergence free. So, you see that incompressible flow imposes a certain restriction on the velocity field, that any field means basically you can say just a mathematical function, okay, function of spatial position and time, that any function that you can choose cannot be a possible candidate for the velocity field. Only those which are solenoidal, which satisfies this relation divergence of u equal to 0, can be an possible candidate for description of the velocity field. So, not any field can qualify as velocity field for a constant density flow. For a constant density flow, the velocity field has to be solenoidal or divergence free. So, it is basically a restriction imposed on the possible solution that will come. We forgot to define something called a stream tube. When we define streamlines, it is another concept. A stream tube, think about a closed curve. A closed curve is made up of infinite number of points. Through each point we can have a streamline. Okay. Now, if we think about a closed curve and then through each point we have the streamlines, then it forms a tube. All those lines together they forms a tube. This is what is called stream tube, a tube made up of streamlines. That means, if we draw the streamlines passing through all the points of a closed curve, then the resulting tube, that is the stream tube. This divergence free velocity field needs that the stream tube cannot end anywhere, either at the boundary, it can end only at the boundary, or it can make a closed curve, or it can extend up to infinity. Okay, that is the boundary. If there is no other boundary, then infinity. That is also a meaning of this divergence free condition, divergence of u equal to 0, that a stream tube cannot end within the fluid. It has to end either at the boundary of the fluid, which may be infinity, or it can end in itself.